Hello, everyone. My name is Brian Arbic. I'm a professor in the Department of Earth and Environmental Sciences at the University of Michigan. I'm the co-founder of COESSING, the Coastal Ocean Environment Summer School in Ghana. And tonight, it's nighttime here, I'm going to give a lecture on tides, which is one of my research specialties. So I'm going to first show an animation to give you a visualization of what's happening. I'm going to start by talking about what's happening on the left. So this is an animation of M2 tidal heights. So M2 stands for moon twice daily. It's the largest frequency in all of the tidal lines of the ocean. It has about 2/3 of the energy. And these are simulations done with the Hallberg isopycno model. Robert Hallberg is a scientist in the NOAA Geophysical Fluid Dynamics Laboratory, and he was one of my collaborators when I did these simulations a long time ago in the early 2000s. So this is a computer simulation of M2 tides at 1/4 degree global resolution. We can do much higher than that now. And let's talk first about the sea surface height anomalies on the left. So anomaly means departure from average. So you see there's red colors and there's blue colors, and they move around. The red you see as positive and the blue is negative. So that means that the red is a high tide, so the water is higher than average. And the blue is a low tide, it's lower than average. And you can see that these propagate around. So here we're red. And now we switch over to blue. And it propagates around in a direction that's counterclockwise in the northern hemisphere. So if you took a course in geophysical fluid dynamics, you would be able to prove that gravity waves, which tides are, in the northern hemisphere propagate counterclockwise along boundaries. So gravity waves propagating along boundaries are known as Kelvin waves, after the famous scientist Kelvin, who first solved that mathematical problem. The horizontal scales are larger in the open ocean than they are in coastal oceans. There's reasons for that. That has to do with the size of these waves is approximately given by the square root GH over F, where G is gravity, H is the ocean water depth, and F is the Coriolis parameter. So since it goes like square root of the depth, that's why they're larger in the open ocean than they are in coastal areas. Now, you might be wondering as you're looking at this, what's going on in the right. So let me explain that. So these tidal elevations going up and down are associated with currents. And this makes sense because if you have tidal currents coming together at a point like this, that's called a convergence. That's going to be driving mass into that area and sea level will go up. On the other hand, if you have a divergence and the currents are being pulled apart like this, that will bring the sea level down. You'll have a low tide. So you have currents associated with the tidal elevations. Suppose those currents encounter a topographic obstacle, such as the Hawaiian island chain. Then that's going to cause vertical motions. Now, the ocean is stratified. So in this simulation, we made an incredibly simple oversimplification of that. We said, let's presume that the ocean has 2 layers. One layer that's very light and a layer below it that's very dense, and an interface between them. So if you have vertical motions for the reasons I described earlier, that interface will move up and down at tidal frequency. And so that is what you're seeing on the right, the interfacial height anomaly. These are called internal tides. So this interface in this particular simulation was at 700 meters depth. So at 700 meters depth, that interface was moving up and down. Notice that the scale goes from meters to decimeters from left to right. So it's much larger vertical motions of that interface than you get at the sea surface. It's tens of meters instead of just meters. The horizontal scale is also much smaller. So in fact, most of the research in our group is done on these kinds of simulations, but now in a more modern context. I think I said these simulations here were done almost 20 years ago. So now we use much larger computers, and we refine these with many more layers in the vertical, much higher resolution. And I talk a little bit about that in my 5-minute research talk about this kind of stuff, doing this at much higher resolution. But for the rest of this talk, I'm just going to talk about the fundamentals of what sets up the tides as you're seeing here. So let me now return, with that as an introduction, let me now return to this main lecture, and I will make it full screen and give the lecture. So as an outline, we're going to talk about the equilibrium tide. We'll talk about lunar versus solar versus sidereal days, the spring neap cycle, the concept of declination and diurnal tides. We'll talk a little bit about harmonic decomposition, tidal species, Laplace's tidal equations, the tidal response to astronomical forcing, and coastal tides. So by way of motivation, although the study of tides dates back all the way to Newton, they remain an important part of physical oceanography. Satellite altimetry, these are instruments that fly over the Earth and measure sea surface heights through remote sensing. So for instance, the ones that are up there now send microwaves down to the Earth's surface, which then travel back. And so if you have a high tide or a low tide, then that travel time will change, and they can use that to see whether the sea surface is higher or lower than average. So satellite altimetry has revolutionized our understanding of tides by producing, amongst other things, accurate global maps of tidal elevations. Tides are also an important signal in current meter data. If you measure currents in the ocean, you will see the tides. Tide gauge records of sea level, same thing in other instruments. So they're still important. You see them in satellites, you see them in other types of data in instruments that are placed in the water. Obviously, they're important for navigation. Ships need to know whether the tide is high or low, whether the tidal currents are going in or out. And tides are also an important source of mixing in both the coastal and open ocean. So by mixing, we mean that those internal tides that I showed earlier, they can turn over just like waves on the surface, and that causes a lot of turbulent breaking and mixing. And that's the way the ocean loses its energy and mixes waters of different temperatures together. So what about the equilibrium tide? Tidal forces are due to the differential force of gravity across a body of finite size. For instance, the Earth rotating around the center of mass of the Earth-Moon system. So the next 5 slides give a cartoon view from a lower level oceanography course. The textbook is Essentials of Oceanography by Trujillo and Thurman, so a few plots from their book. So the Earth system, Earth-Moon system rotation. So here's the Earth, and here's the Moon, and the Moon is orbiting around the Earth, and in turn, the Earth is orbiting around the Sun. And so the barycenter, which is the center of mass of the Earth-Moon system, is rotating, revolving around the Sun. So there's a lot of things, the Moon's orbiting around the Earth, and the whole system is orbiting around the Sun. And so the center of the Earth is orbiting around the center of mass of the Earth-Moon system, or barycenter. And the barycenter is displaced from the center of the Earth a little bit because the Moon, of course, does have mass. And so the center of Earth revolves around the barycenter, and of course it has to take the rest of Earth with it. So basically, the whole Earth is basically doing this. It has a radius that's equal to the distance from the center of the Earth to the barycenter. Okay? And we'll get back to that, the importance of that. So gravitational forces, the gravitational force is largest on the side of the Earth closer to the Moon, and it's least on the side furthest from the moon. And the force is always directed towards the center of the moon. Now, there are centripetal forces that are due to the rotation around the barycenter or center of mass. And this is everywhere the same because the whole Earth is basically doing this. And so the red arrows are all the same length and point in the same direction. So the tide producing forces, they're the differences between the centripetal and gravitational forces. So the tide generating force in blue is the difference of the moon's gravitational force in black and the centripetal force in red. So for instance, let's take this point that's closest to the moon. So you have a stronger gravitational pull. There's the centripetal force. And if you take the difference between this and this, you have this blue arrow pointing towards the moon. On the other hand, at the other extreme, on the other side, the gravitational force is weaker because you're farther from the moon. And so the difference between the gravity and the centripetal force then gives you a negative result. So it's pointing away from the Earth. And that basically means that both on the side facing the moon and on the other side, you have a tidal force that's pulling out like this. So you have high tides on both the side facing the moon and on the other side. And so you have these tidal bulges in an ideal Earth covered by the ocean, both on the side facing the moon and on the other side. And so the tidal cycle results from the fact that the Earth is rotating underneath these bulges. So it's going to see a high equilibrium tide when it's underneath the moon and on the other side, and in between those, it's going to see low tides. So as it rotates during a day, it's going to see 2 high equilibrium tides and 2 low equilibrium tides. So this simple shape, the equilibrium tide, is also sometimes called the tidal forcing. And so the actual tide in the ocean doesn't look like this. Remember the movie we showed? It didn't look this simple. It's just a bunch of highs and lows. But the actual tide in the ocean is a complex response to the forcing of the equilibrium tide. Okay, so a little bit of math for those that like math. So all points on Earth experience the same centripetal force per unit mass due to the motion around the center of mass of the Earth-Moon system. So that's given by G, which is Newton's gravitational constant, m moon, which is the mass of the moon, and r divided by r squared, where r is the distance from the center of the moon to the center of the Earth. On the side of the Earth closest to the moon, you basically take this same formula, but now instead of having r squared in the denominator, you have r minus a squared, where a is the radius of the Earth. Because see, now if this is the center of the Earth and this is the center of the moon and that distance is r, then when you're at the point of Earth that's closest to the moon, it's this much closer to the moon, where this much is a, the radius of the Earth. You can see that in this drawing here, that see if here to here is r, then here to here can't be quite r because it's this much closer to the moon, and that distance is a, the radius of the Earth. So it's r minus a squared. And so the tidal force is the difference of the gravitational and centripetal force. So that's gm moon times 1 over r minus a squared minus 1 over r squared. And then you can write that as gm moon over r squared minus 1 here, but over this thing. But this part here, you use the fact that r is much greater than a. So r squared minus a, r minus a quantity squared is r squared minus 2ar plus a squared. But because a is very small, that plus a squared we neglect. So then you can write this as 1 minus 2a over r. Then what you use is the fact that again, a is much less than r. So this quantity here is much less than 1. So you use the fact that 1 over 1 minus a small number is basically the same as 1 plus that small number. So then this whole thing becomes 1 plus this, and 1 plus this minus 1 is 2a over r, and 2a over r times this gives you this quantity here. And then on the side of Earth farthest the moon, it's the same math, except now it's 1 over r plus a squared. And so you do the same kind of math, and now you get a negative sign. The force is equal but opposite, yielding 2 bulges in the equilibrium tide. So note that the force goes like r cubed. So this is something that is very interesting. You might call it the raw gravitational force of the tides. Sorry, the raw gravitational force of the moon on points on Earth goes like 1 over r squared. And that's what's responsible for the whole Earth moving like this, in a radius that's equal to the distance, again, from the center of the Earth to the barycenter. But because tides are due to the differences in forces, and because if you differentiate 1 over r squared, you get 1 over minus 2 over r cubed. That's why the tidal forces go like r cubed, inverse r cubed. So the same reasoning applies to the sun's gravitational field on Earth. The sun should also cause tides. If this was a live lecture, I would ask you to all raise your hands. How many of you think that the solar tides are larger versus the lunar tides? So I'm actually going to pause for a second, so because this is an online experience, you could think about that a little bit before I tell you the right answer. So do you think the solar tides are larger, or do you think the lunar tides are larger? Okay, so the sun is 27 million times more massive than the moon, but the distance from the Earth to the sun is 390 times the distance from the Earth to the moon. And this tidal force goes like 1 over r cubed. So you take 27 million and divide by 390 cubed, put that in your calculator and test it out. You're going to find that it's 0.45. So the sun loses to the moon. It's less than the moon when considering differential gravity, which is the cause of tides. So the solar tides are very important. 0.45 is not a small number. It's almost half. But the tides caused by the sun's gravity are smaller than the tides caused by the moon's gravity. So the next question, is the period of the principal lunar tide equal to that of the principal solar tide? So again, if we were all together in person, I would ask for a show of hands, but just think about it a little bit. Do you think that the periods of the lunar and solar tides are equal or not equal? So I'll pause for a second. Okay, so the answer is they're not equal, and they're not equal because lunar days and solar days are different from each other. So first I'm going to say some words, and then I'll show some pictures that I think will make it easier to understand. So the moon orbits the Earth, and while the Earth is rotating around its axis, the moon moves relative to the Earth because, again, it's orbiting. So therefore, it ends up taking 24 hours and 50 minutes for an observer on Earth to see subsequent moons directly overhead. And so a lunar day, which is defined by looking at the moon, is 24 hours and 50 minutes. And that means that the high lunar tides are 12 hours and 25 minutes apart. And the period of the, which is half of this, 24 hours, 50 minutes. So the period of the principal lunar semidiurnal tide is 12 hours and 25 minutes. On the other hand, it takes 24 hours for an observer to see subsequent suns directly overhead. So what we normally call a day is actually a solar day. And so the high solar tides are 12 hours apart, and the period of the principal solar semidiurnal tide is 12 hours. So they're slightly different for this reason. So here's a picture that might help you understand if you didn't quite follow everything I said on that last slide. So here's an observer on Earth. So here's a person on Earth. They're looking up and they see the moon. and then the Earth rotates. So the observer is moving around like this. And by the time the observer gets back to this spot, 24 hours later, the moon has moved because it's moving in its orbit. So then it takes a little bit longer for us to catch up and see the moon directly overhead again. So that's why a lunar day, which is a day defined by looking at the moon, is different than a solar day. So now, again, we can talk about some words, and then I have a picture. So we can think about what happens when the Earth, Moon, and Sun are in a line versus when they're not in a line. So spring tides occur when the Moon, Earth, and Sun are aligned. They're in what's called syzygy. That's a special word that means the Moon, Earth, Sun are in a line. And so syzygy is when they're all in a line, and that occurs during a new moon or a full moon. And so when this happens, the equilibrium tide pulled by the moon, the lunar equilibrium tide, and the one pulled by the sun, the solar equilibrium tide, are lined up. So you get exceptionally high highs and exceptionally low lows. The tidal range, or the difference between high and low tides, is large. Now, neaptides occur when the Earth-Moon line is at right angles to the Earth-Sun line. And so, again, there's a diagram on the next page that shows this. So then in that case, the sun's bulges do not reinforce the moon's bulges. So the tidal range is lower. The high tides are not as high. The low tides are not as low. This occurs during the first or third quarter moons. Now, the spring tides occur twice per lunar month. So despite the word spring, it has nothing to do with seasons, spring, summer, fall, winter, because it happens twice every month. So I'm not a specialist in the study of words, but my understanding is that the reason they call it spring tide, it's a very old English word, is that it appeared that the tides were springing out of the earth because they were exceptionally large. And then the neaptides are also twice per lunar month. That's, again, when the difference between highs and lows is not so large. So here's a picture, you see. So when the sun and the moon and the earth are all in a line, which happens during both new moon and full moon, then you see the equilibrium tide pulled by the moon and the sun are all acting in the same direction. So you get an extra high equilibrium tide and an extra low equilibrium tide. So the tidal range, the difference between high and low, is at its greatest. On the other hand, during a neaptide, then you see the equilibrium tide pulled by the moon and that pulled by the sun are not acting together. They are not acting together. And so the high tides are not as high and the low tides are not as low. Now, the next concept we have to talk about is declination. So diurnal tides are due to the declination of the moon's orbit to the equator. The declination yields asymmetries in the two high tides that occur every day, and mathematically, this is like having a forcing at once per day. So where's the picture for that? So here's declination. So here's the equatorial plane of the Earth, and then the Earth is spinning, of course. And the moon is tilted with respect to that equatorial plane by as much as 28.5 degrees. And that's basically because, by the way, it's because there's a plane of the solar system called the ecliptic that most of the planets and things are in. And the Earth's spin axis is tilted with respect to that plane by 23.5 degrees. That's called obliquity. And the plane of the moon's orbit to the ecliptic is tilted by 5 degrees. So if you take 5 degrees and add that to 23.5 degrees, you get 28.5 degrees. So what that means as the Earth is spinning is that this equilibrium tidal bulge is tilted with respect to the equator. And so if you're an observer here, you're going to see an exceptionally high equilibrium tide at this time of the day, but when you get over here, you're still going to see a high tide, but it's not as large, and it's because of this tilt of the moon to the Earth's equatorial plane, which again is due to two things. The lunar orbital plane is tilted with respect to the ecliptic by 5 degrees, and the Earth's spin axis is tilted by 23.5 degrees. You get the same effect with the sun there, but then it's only due to obliquity, 23.5 degrees. So every day there you see two high tides, but they're unequal. So this is known as the diurnal inequality. And these two high tides a day are of unequal sides. So mathematically, that's like having a tidal forcing at periods near 24 hours. And that gives you diurnal tides. So we're now ready to talk about the harmonic decomposition. So basically the tides are, there's many tidal lines. If you do a frequency analysis of sea level or currents, you'll see all these tidal lines, and the frequencies of them have to do with frequencies of celestial motions. So let's let omega naught be 2 pi over 1 mean solar day, in other words, 24 hours. And let's let omega 1 be 2 pi over 1 mean lunar day, in other words, 2 pi over 24 hours and 50 minutes. And let's let omega 2 be 2 pi over a sidereal month, and omega 3 be 2 pi over a year, and then there's many other frequencies of celestial motion. So the frequencies of the tidal constituents are basically multiples, sums, and differences of these basic tidal frequencies. So for instance, M2, the principal lunar semidiurnal tide, has a frequency of 2 omega 1s. So it occurs twice per lunar day, because omega 1 is associated with lunar day. Similarly, S2 is 2 omega naught, twice per solar day. K1, which is the largest diurnal tide, and because it's once per day, it has a 1 instead of a 2 subscript. That has a frequency that's equal to the sidereal frequency. In other words, the frequency associated with the period of a day as defined by the distant stars. So if you look at the distant stars and then the Earth rotates and then you see the same distant star again, that's 23 hours and 56 minutes. It's not the same as a solar day or a lunar day. And so the sidereal frequency can be obtained by either adding omega naught plus omega 3, in other words, a solar day and a year, or omega 1 plus omega 2, in other words, a lunar day and a month. And that means that K1 is forced by both the moon and the sun. And then the fortnightly tide is twice per month, 2 omega 2. And there are many others. There's actually hundreds of tidal lines. And so another way to understand the spring-neap cycle, aside from that syzygy diagram I showed earlier, is that it's a frequency beating phenomenon. So those of you who study these things, you know that if you have two sine waves of nearly similar, not similar but not exactly equal frequency, they'll come into and out of phase, thus giving you very high highs and lows at some times versus a compressed high-low range at other times. Okay, so tidal species. So there's semi-diurnal tides, there's diurnal tides, and there's long period tides. And so the four largest semi-diurnal tides, we've already talked about M2 and S2, the principal lunar and solar semi-diurnal tides. There's also N2 and K2. And again, there's actually many, many more. These are just the four largest. So these are the four largest semi-diurnal tides. These are the four largest diurnal tides, K1, P1, and Q1. And the two largest long period tides are called MF and MM. And so the latitude and longitudinal dependence of the equilibrium tide, which we use this symbol eta, equilibrium, depends on the tidal species involved. So for semi-diurnal tides, eta equilibrium, there's an amplitude times 1 plus K2 minus H2, and that will be discussed later, times cosine squared of phi, and phi is the latitude, times cosine omega t plus twice lambda. Omega is the frequency, t is time, and lambda is longitude. So for M2, there's certain values of A amplitude, and this factor 1 plus K2 minus H2, and there's a certain frequency. S2, all of those things, A, 1 plus K2 minus H2 and frequency would be different, and so forth for N2 and K2. So for diurnal tides, it looks similar, but instead of having cosine squared phi, it's sine 2 phi. And instead of having twice longitude, it's only once longitude. So what that means is that if you freeze time, because there's 2 longitude here, that means that as you circle around the Earth, you'll have 2 highs and lows, like we talked about earlier. But for diurnal tides, if you freeze time and then you go all the way around the Earth, you're only going to have 1 high and 1 low, because there's only a 1 factor of longitude, not 2. Then for long period tides, there's yet another latitude dependence, and there's no longitude dependence at all. Now, for those of you who know a lot of math, let me just say that there's a more sophisticated way of understanding the tidal potential. Instead of doing this exercise that we did back here, this stuff here, you can actually go through the math of what's called spherical harmonics, the natural basis functions on a sphere such as the Earth. And if you do that, you will get the spherical harmonics y22, which is this one, the semidiurnal tides, y21, which is this one, the diurnal tides, and y20, which is this one, the long period tides. That's the more sophisticated way of understanding the tidal potential. If you don't really know what I'm talking about, it doesn't matter that much. It's just an aside for those that have more math background. So those tidal constituents that I listed before, here's the values of their frequency, amplitude in centimeters, and their periods. So you see that the semidiurnal tides that have a 2 near them have a period that's close to half per, close to half. So that means half a day, a period near half a day, meaning 12 hours. And so the period is just 2 pi divided by the frequency. So for those that enjoy math, if you take 2 pi divided by this and convert the units from seconds to days, then you'll get this. Now then the 4 diurnal constituents with subscript 1 have periods near once per day, and then the long period tides have much longer periods. And the amplitudes, you can see right here that M2 has the largest amplitude, S2 also has a large amplitude, and then N2 and K2 are smaller. K1 and O1 have amplitudes that are almost as large as S2 in the equilibrium forcing. But the response is actually slightly lower. So now, are there any factors that you can think of that would prevent the actual ocean tides from attaining the equilibrium state? So in other words, so far we've mostly been talking about the equilibrium tides, this simple shape here. So just think about this a little bit. If we were in the classroom, we'd actually have a discussion. But do you think that the real tide can equal this thing here? Or are there factors that prevent that? So I'll pause for a minute. So one thing you might think of is that the continents are in the way. So that simple shape can't just propagate all the way around the Earth, because not all of the Earth is ocean. You have oceans and then you have continents, and that shape cannot just flow over the continents. There's no ocean there. So that's one thing. The continents are in the way. There we go. But there's other things. So the Earth is rotating, and because it's rotating, there's a force called the Coriolis force. I hope in one of the lectures that someone else is giving in this for this school, the Coriolis force will be explained. But if not, you can Google it. You can go to the web and just type Coriolis force and learn about it. It's a force on flows in the atmosphere and ocean that's due to the fact that the Earth is rotating. There's also friction. And here's another interesting thing that I assign as homework when I teach this at University of Michigan, but I'll just explain it for those that want to try it. So the speed of gravity waves is the square root of g times the depth. G is 9.8 meters per second squared, and the average depth of the ocean is about 4,000 meters. So put that in and you'll find that the speed is about 200 meters per second. And then calculate how fast the moon is moving over the Earth. So in other words, if you're at the equator and you see the moon overhead and the moon is circling all the way around, so that's 2 pi times the radius of the Earth. The circumference of a circle is 2 pi r. You multiply that and you divide by 24 hours and you'll find the speed of the moon moving around the Earth, and compare that to the speed of the waves. And what you'll see is that the waves are not traveling fast enough to keep up with that wave. So even if there is no friction or other complications, even if it was just a water world, you still wouldn't have the tides equal to the equilibrium tide because the waves are not fast enough. And in fact, the real ocean tide is a complicated response to the equilibrium forcing due to the fact that you've got all these complications. And again, go back to that movie I showed at the very beginning. The real tides are these complicated shapes that they look a lot more complicated than those simple bulges. And in fact, in some locations, the dominant tide is diurnal. It's once per day, not twice per day. And so here we're looking at some monthly tidal curves. So here's a place, Boston, Massachusetts, where the tide is predominantly semidiurnal. So you can see a lot of things going on here. So here's a high tide, here's a low tide. Here's a high tide, here's a low tide. Notice, by the way, that during the neap tide, the difference between the highs and the lows is not as great as it is during a spring tide. That's one of the concepts I talked about earlier. So you have the neap tide and the spring tide, but here we also want to point out that basically there's 2 high tides a day and there's 2 low tides a day. And if you look at these high tides here and the low tides here, they don't look very different. And here too, these 2 next to each other, highs next to each other, these 2 lows next to each other, they don't look very different. At the other extreme, this place in China has, it of course also has a spring neap cycle, but notice how it looks stretched out in the horizontal. You see how it's stretched out in this direction here compared to here. That's because there's basically only 1 high tide per day and 1 low tide per day. So that's a place where the tides are predominantly diurnal instead of semidiurnal. And then most places in the world are mixed diurnal, semidiurnal. So like San Francisco, for instance, has 2 high tides a day that are noticeably not the same, and 2 low tides a day that are noticeably unequal. And so most places in the world have fairly substantial semidiurnal and diurnal tides. So that means they see 2 highs and 2 lows per day, but they're definitely not the same. So we model the tidal response to astronomical forcing with the shallow water equations forced by the equilibrium tide. And these equations are traditionally known as the Laplace tidal equations. So Newton came up with the concept of the equilibrium tide, which we defined earlier, and Laplace further refined that into the tidal species we talked about, semidiurnal, diurnal, and long period. And he also came up with the Laplace tidal equations. And modern shallow water models basically use a version of Laplace's tidal equations that looks something like this. So ddt, that's the partial derivative with respect to time of the velocity. That's this term, partial u, partial t. That's called the tendency term of velocity. And then this is called advection. And explaining that would take a while, but if you're interested, you can Google advection, a fluid mechanics advection or something like that, or hopefully one of the other lectures will explain that. This is the Coriolis force due to Earth's rotation. This is Earth's gravity. This is a spatial gradient operator, partial partial x, partial partial y, partial partial z. Eta is the departure of the sea surface height from average. And here is the equilibrium tide we talked about earlier. So the equilibrium tidal forcing is, and then there's a friction term, of course. The equilibrium tidal forcing is very important. It's what drives the tides. But the actual tidal elevations here and velocities here are a dynamical response to the equilibrium tidal forcing. Whenever the elevations and the equilibrium tidal forcing are not equal, and they never are, then you take the spatial gradient of that difference, and that is what drives the system. And then, so this is a momentum equation because it's talking about forces. There's also a mass conservation equation, and I talked about this earlier. If you take the water column thickness, which is the resting depth h plus the perturbation of the sea surface height eta, you take that and multiply by the velocity, then that's kind of a mass flux. You're driving mass because you have a velocity acting through that water column. And when you have a divergence of that, then you cause a change in the sea surface height. So pictorially, it goes like this, and I mentioned this earlier. If you have a convergence of mass flux, it's going to cause sea level to go up. And if you have a divergence, it's going to cause sea level to go down. And this equation here is just a mathematical statement of that fact. In recent forward tide models, friction includes eddy viscosity, so the viscosity due to small scale turbulence, quadratic bottom drag, which is a drag coefficient divided by the resting depth times UU, the velocity squared. And it acts in the direction of the velocity. So you take the magnitude of the velocity times the velocity itself. It also has a term due to the energy conversion into internal waves over rough topography. So I mentioned that earlier, that flow over topography creates internal waves. I showed a movie of that at the beginning, and that those waves eventually turn over and break, and that causes mixing. Again, note that the equilibrium tide is the reference which the sea surface elevation zeta are measured against. And the equilibrium tide is a perturbation to the geoid or equipotential. So when we go into our supercomputing codes, our equations are actually more sophisticated than this, because there's another term called the self-attraction and loading, and there's that all these frictional terms I mentioned. There's also stratification, many layers, and there's also, in some of our models, other motions, not just tides, but other motions all interacting. The equations could get more complicated, but this is the essence of tidal modeling. So if you put equations like this or more complex versions of it in models, you will get those tidal motions that I discussed earlier. Now, it's one important concept of tides, because they're periodic, is we can make amplitude and phase maps of them. So for each constituent, for instance, the tidal elevation as a function of latitude phi and longitude lambda can be written as an amplitude at that spot times cosine omega t minus a phase at that spot. And the phase by convention is measured against the Greenwich meridian. So we can construct maps of the amplitude and phase of tidal elevations for each constituent. Note that the spring tidal range is the peak to peak value, which basically is twice the sum of the amplitudes of several constituents. So if you just look at a tidal amplitude, it can be deceiving. You may say a meter, and you might think, oh, the water only goes up by a meter, but that's going up by a meter and then down by a meter, and that's only for that constituent. Once you start adding all the constituents together, you can often get a much bigger range than that. So Here is a map of the M2 amplitude and phase, and here's the K1 amplitude and phase. So the phase is basically telling you about timing. So remember that movie I showed at the beginning, those blobs were traveling around. So that means that you would see a high tide here, and then it travels past, and then you see a low tide. So this is basically telling you when the highs and lows come at particular points, when that blob of high is moving versus the low. And the amplitudes are telling you just how high or just how low it can get for that particular constituent. So the dark colors are very high amplitudes, which tend to be mostly near coastal areas or in coastal areas. And here's for M2 and here's for K1. So if you go back to this plot here, look at Boston, Massachusetts. That was predominantly semi-diurnal. And so you look along the US East Coast where Boston is, and it has a very low diurnal amplitude. And so again, the actual tides, which are shown here, are a complicated response to the forcing. And so it just turns out, as part of that complicated response, that the Atlantic Ocean does not have very large diurnal tides, which is why, whereas it does have large semidiurnal tides, which is why a place like Boston sees predominantly semidiurnal tides. On the other hand, if you look at, say, San Francisco, then San Francisco's on the US West Coast. It has large diurnal tides, you have the red colors there, and large semidiurnal tides, so that's why you see a mixed pattern. So here's showing those curves again. You can see them a little better. So Boston has 2 high tides a day and 2 low tides a day, and they're always pretty similar, but they can be modulated over the spring neap cycle, as we discussed earlier. Whereas San Francisco, you see 2 high tides a day that are unequal and 2 low tides a day that are unequal, and that's because both the diurnal and semidiurnal tides are large near San Francisco. Now in coastal tidal areas, the largest tidal elevations or height changes and largest tidal currents, they're found in coastal areas. So typical tidal current values can be up to 1 meter a second in coastal areas, whereas they're only about 2 centimeters a second, about 50 times smaller in the open ocean. And the typical values of constituent elevation amplitudes, again, they're maximum a meter in the open ocean, often much less. They can be up to 4 meters in coastal areas. And again, remember that that's for one, like M2, it goes up 4 meters and down 4 meters. So the peak to peak is 8 meters. And then when you add all the other constituents in, you can maybe double that again. So you can get pictures like this. So there's a couple places in Canada, the Bay of Fundy and the Hudson Strait, where the spring tidal range, so that's the difference between high and low during spring tide, which is when you have the highest range, it can be 17 meters, which is about what is that? About 56 feet. And so boats actually sit in the mud during low tide. You see here's a place where the tidal range is so large that the boat is now sitting in the mud during low tide. So I think that's the last slide. And I would like to mention one thing that I thought I was going to get to but didn't, and that is when, I said that I said here the factor 1 plus K2 minus H2 would be discussed later. So the astronomical forcing applies not just to the water, but also to the planet Earth. So the planet Earth is moving in and out due to tidal forcing, and that's called a body tide. And the reason that matters for ocean tides is that the seafloor is moving up and down, and the water column thickness is measured against that seafloor. And this number H2 accounts for that. And because the Earth is doing this, the self-gravity of the mass on Earth is actually changing the gravitational potential, and that's what this number here is accounting for. So these numbers here are called Love numbers after the English scientist Love, who came up with this idea. And 1 plus K2 minus H2, it depends on the frequency, but it's around 0.7 for almost all the major tides. And so that means that if the Earth was perfectly rigid and didn't do this, then the ocean tides would actually be about 30% larger than they are. And then there's another even more complex thing that arises called self-attraction and loading. Basically, the self-gravity of the tide on itself changes the gravitational potential. The load of the ocean tide compresses the Earth. That's different than the body tide, which is a direct response to astronomical forcing. And then the gravitational potential, the self-attraction of the deformed Earth changes the gravitational potential. So all of that together is called the self-attraction and loading. And so there's another term in this equation that accounts for the self-attraction and loading. So let me just finish by going back to our movie here. And just remember that this shape of the tides, which can be converted into the amplitude phase maps that I show here, is due to the complex response of the ocean, the friction, tides in the Earth, Earth is rotating, continents get in the way, all that stuff. It's due to the complex response to the astronomical forcing. And if you put all this into a computer model, you can actually model this. So I think that's good enough for now. And if any of you have any questions, you can come to my Zoom office hours. So thank you very much. And I hope you enjoy the Coastal Ocean Environment Summer School in Ghana this year. Thanks.